In the past, the world of assembly programming was filled with ingenious tricks to save even a single clock cycle. Multiplication was considered a luxury, and skilled programmers relied on addition and shift operations instead. Shift operations involve moving bits left or right within a number, effectively enabling fast multiplication or division by powers of 2. On processors, without a multiplication instruction, doubling a value meant shifting left once, quadrupling meant shifting left twice, and so on. Division could also be achieved using right shifts, making shift operations a fundamental technique for integer arithmetic. Even zeroing out a register had its own optimization techniques. The obvious approach was to load an immediate value of 0, but a more efficient method was to use an XOR operation. XORing a register with itself always results in 0, eliminating the need to fetch an immediate value from memory. This trick, especially common in x86 processors, was a staple of efficient assembly programming. Branching, too, was an area where optimization was crucial. Programs execute different instructions based on conditions, but every jump instruction disrupts the flow of execution, leading to performance penalties. To mitigate this, programmers carefully structured conditional jumps to maintain sequential instruction flow as much as possible. In an era without branch prediction, excessive branching directly led to slower execution, prompting the development of techniques that reduced unnecessary jumps by leveraging loops and flag manipulations. One of the more advanced techniques was self-modifying code. This approach involved modifying program instructions during execution to eliminate the overhead of loops or conditional branches. In early computers with limited memory, this technique provided flexibility and efficiency. However, with modern CPUs utilizing instruction caches, self-modifying code often results in cache invalidation, making it counterproductive and rarely used today. Negative flags were another tool for optimizing calculations. Subtraction is typically performed by inverting a number's sign and adding it using 2's complement arithmetic. The neg instruction allowed programmers to achieve this in fewer instructions than a standard subtraction, streamlining operations. By strategically controlling processor flags, unnecessary comparison instructions could be eliminated, ensuring smoother execution. Today's CPUs have far surpassed these past limitations. Superscalar and out-of-order execution allow multiple instructions to be processed in parallel. Multiplication completes in just a few cycles, branch prediction has become highly accurate, and conditional move instructions eliminate the need for many jumps. There is little need for manual micro-optimizations at the instruction level. Still, not all optimizations have become obsolete. In embedded systems using RISC-V or ARM architectures where instruction sets remain simple, shift operations and branch reduction are still valuable techniques. In environments such as GPUs and FPGAs where parallel processing is prioritized, minimizing conditional branches remains crucial. Above all, cache optimization continues to be one of the most impactful tuning strategies, even in modern computing.